H2 gas gets removed. Though, and we did the graph method, which was that you measure the change with respect to time. Initially, the change happens very quickly and then it slows down, then becomes constant. That means the reaction has stopped, right? And the gradient represents the rate. So any change, whether it's an increasing change, decreasing change, the gradient, the direction or the sign of the gradient is not important. The value or the steepness of the gradient is important. Now, and then we talked about that you can measure rate without graph, that what you can do is you can keep the change constant. Like you can keep it fixed that what is the amount of time that it takes for 5 cm cube of H2 gas to get produced. So rate would then be inversely proportional to time only. As we talked about factors affecting rate, and we started talking about the order of a reaction, right? So this is we did this part. So what was the order? That if you have a reaction where you have A and B reacting together and C is getting produced, then your rate would be dependent on the concentration of A and it will be dependent on the concentration of B. You increase the concentration, the speed of the reaction would normally increase. So rate is proportional to the concentration of your reactants, which are these. TK Varda, is this clear?
Yeah.
And X, the power X or power Y is the order. I told you that if you have, I remember that the rate equation could also include catalyst. Sometimes the rate is also dependent on the concentration of catalyst. So your rate can be dependent on the concentration of the catalyst. Or even the products. Sometimes what happens is that the product also changes the rate of reaction. That's an autocatalytic reaction. Autocatalytic reaction is that as soon as the product is formed, the product is acting as a catalyst. Is this clear? Was that clear?
Could you please repeat the last point?
I mean, the last point was that I said that the rate is dependent on the reactants, right? But I also added that sometimes what happens is that the rate is also dependent on the catalyst. So maybe the catalyst concentration is also part of the rate equation or relationship. And sometimes the product also affects the rate of reaction. That as soon as the product is formed, the product starts acting as a catalyst and starts speeding up the reaction. So that's known as an autocatalytic reaction, that whatever is formed, it actually starts acting as a catalyst. Is that clear?
Yeah.
And then I explained to you that rate is dependent on, normally it's dependent on your reactants, right? So if you want to just investigate rate with respect to one reactant and what is the relationship, you want the other reactant to be constant. Its concentration to be constant, which is not constant throughout the reaction. So what you do is that you keep it in large excess. When you add something in large excess, then practically speaking, it kind of becomes its concentration kind of becomes constant. Because if a small amount gets used up, since you're using it in large excess, the amount of concentration hardly changes. It barely changes. So if you want to keep a reactant constant, just put it in large excess. As उसके बाद we did I told you that there's a thing called order 1, which is that a rate is dependent on the reactant concentration and the power is 1, which means that this is a direct proportionality. कि अगर A की concentration जो है ना वो, if you reduce it, the rate will also get reduced. If you increase A's concentration, the rate would also increase. So that's directly proportional, and the graph would look something like this. That if you were to plot A's concentration with respect to time, the reactant will get used up. As it gets used up, the reaction slows down. So the gradient becomes less steep. So it takes longer time for the reaction to happen. So it always has a constant half-life. This is the half-life. Time required for the concentration to decrease by half. Every time, second time, the concentration decreases by half. This is the time. So it's always, so ये graph clear, and is this clear that what's a order one reaction, right?
Yeah, it's clear.
So there's actually another graph as well, which sometimes appears, and that graph is that it's A concentration versus rate. So that's a direct proportionality graph. Okay, you keep on increasing A's concentration, the rate would keep on increasing. Or you keep on decreasing A's concentration, the rate would continue to decrease. And the second one was order zero, which was that the rate is dependent on the A's concentration, but the reactant concentration, the power is zero. That basically means that whatever happens to A, nothing changes, nothing really changes. So that means कि अगर A की concentration जो है ना, that's decreasing, right? Rate would not slow down. So the steepness or the gradient of the graph would kind of remain constant. And so the reaction would just continue at the same speed until it stops. TK, that's clear as well, right? Clear?
Yeah.
Or zero order reaction में ना, the if I plot a rate versus concentration of A graph, then that would probably be a straight line, which basically means the rate remains completely unaffected, no matter what happens to A's concentration. And order two was that rate is dependent too much on A's concentration. That's order two. That means that if you double A's concentration, the rate quadruples, triple it becomes 9 times. You halve it becomes 1/4. So in this case, what happens is that if A gets used up, the reaction slows down too much. So every time the half-life continues to double, it takes a longer time for it to actually, for the concentration to decrease, because the reaction is slowing down by twice the order. अगर उसको half करोगे, it's going to become 1/4. So it's going to take a much longer time, and so the half-life continues to double. ठीक है, ये भी clear है?
Yeah, it's clear.
So now we're going to link it with the second part, which is that the reaction mechanism and like why do you have different orders, right? So this one is that so order one is clear, like you increase the concentration, the reaction speed increases. Normally everything is order one actually. Okay? Order zero and order two are certain cases where you have order zero and order one. So for example, I've got this reaction, which is that there's NO or 2NO reacting with Br2, and it produces 2NOBr. Now that's kind of a simple reaction, right? And it has two reactants. It's got NO and it's got Br2. So we know that your rate of the reaction would be dependent on NO's concentration, and it would be dependent on, I mean, you got two reactants, right? You don't know what the order is. You don't know how they're dependent, but you pretty much know that you got two reactants. You increase NO's concentration or you increase Br2's concentration. So either one of them, it's going to speed up the reaction, right? So this is the overall equation. But now we've got a problem, and the problem is that how to determine the order. Why do you have different orders? The reason you've got different orders is that reactions have certain mechanisms that they follow. So for example, this reaction, it happens in steps 1 and 2. So in step 1, what happens is that so what happens in step 2 is, step 1, sorry, is that NO comes along, reacts with Br2, ends up producing NOBr, and one Br atom gets broken away. And then there's step 2. Then another NO comes in, and the Br that has already broken away, it goes and reacts with this other NO and it forms the second NOBr. Is this clear? That's a simple mechanism, right? Clear mechanism, it's just a random mechanism. Is that clear?
Yeah, it's clear.
Just like your organic chemistry mechanism. So reactions don't happen in just one go. They've got different steps. So now the two steps probably don't have the same speed, which basically means that maybe the first step is a slow step, and maybe the second one, maybe the second one is a fast step. So different steps have different speeds. Now let's say the slow step is taking 100 seconds, and the fast step is taking 1 second. बल्कि इस पे ना so let's continue with this. Should I do this one or the other one? Just 1 second. मैंने example गलत लिया. Let me. I'll come back to this example. Just in a while. Let me give you another example. A simpler one. I want to do a. I'll come back to that one. I'll do a simpler one first. Do you remember SN1, SN2 mechanisms? So these were organic chemistry mechanisms. These were a lot simpler. Just a second. So you had a halogenoalkane. And it's a tertiary halogenoalkane. And it would react with hello, Varda, can you hear me?
Yeah, I can hear you, but I can't see the screen anymore.
Just a second. Sorry, I was just 1 second. You can see the screen, right?
Yeah, I can see it now.
So I just switched to another mechanism. So there's this reaction, which is a halogenoalkane reaction. What simply happens is that your halogenoalkane loses the Cl, and the Cl gets replaced by OH ions. So it's a simple mechanism that the Cl gets replaced by OH ions. Now this reaction has two steps. There's a step number 1. In step number 1, what happens is that your tertiary halogenoalkane has got a Cl, and this Cl over here, it breaks off. Okay, that's step number 1. Now, step number 2 is that as soon as the first step happens and the Cl has broken off, a carbocation is formed and an OH ion comes along. And it joins with the carbocation. Okay, is this clear? Does that make sense that the Cl broke off first? Carbocation gets formed, the carbocation attaches to the OH ions, and you got your alcohol. Okay, to clear a mechanism.
Yeah, it's clear.
So now this reaction has 2 steps. Now, step number 1 is known as your slow step. It takes a longer time for the first step to happen. And your step number 2 is your fast step. There could be a number of reasons why the first one is slow and the second one is fast. One reason could be that, I mean, it would require some collisions to happen before the CCl bond breaks and the Cl gets released. But as soon as the Cl gets released, the carbocation attracts the OH, and so this step happens very quickly compared to the first one. And I'm going to give it a time. Let's say this takes 100 seconds and this takes 1 second. Now think of this as a relay race where you've got 2 runners running, right? One of them is really slow, the other one is really fast. So if you want to speed up your reaction, which one do you speed up? The fast one or the slow one?
The slow one?
Yes, it's obviously the slow one because right now it's taking what, 101 seconds, right? In total, right? So if I were to speed up the fast step, uh, let's say I speed up the 1 second part, and I speed it up so much that it becomes 0.00001 second, right? So the overall speed would still be around 100 seconds. It's not going to be affected that much, right? So the point is that it's kind of irrelevant to increase the speed of the fast one, right? So it's the slow step that has to be speeded up. Well, इसको जितना मर्जी कर लो ना, you're just going to reach 100 seconds. That's it. Is that clear?
Yeah, it's clear.
So the point is that these OH ions, one of your reactants, I mean this one over here, is kind of irrelevant in the mechanism. Okay, OH ion is 0 order. Its concentration is 0 order. Why? Because it's in the fast step. As it's in the fast step. So that's why it's 0 order, that although the reaction will speed up, but it's the fast step that's going to speed up. So no matter how much you speed this fast step up, pretty much nothing happens. Okay, so clear? Do you understand why you have certain reactants that are 0 order? Is that clear?
I don't really understand. Like, what do you mean by it's 0 order?
The 0 order means that you increase the concentration of OH ions, right? Will the overall reaction speed up or not?
If it's 0 order, then it won't speed up.
Okay, do you understand why it's 0 order? Because it's in the step which is the fast step, which is the fastest step. So even if you increase the OH ion concentration, the slow step will not increase, right? Because it's not even involved in the slow step. If I increase the concentration of OH ions, right, your fast step is going to increase. So if your 1 second step speeds up and it becomes 0.1 second, the overall speed of the reaction hardly gets affected, right? Is that clear?
Yeah, that makes sense.
So right now it's taking 101 seconds. No matter what you do, you'll probably just get close to 100 seconds. That's it. So the OH ions are kind of irrelevant. Nothing happens, doesn't really speed up the reaction, right? As a meanwhile, on the other hand, the other reactant, you get this one over here. That's your other reactant. That is first order. First order was directly proportional, that the reactant so this one is first order. Why? Because it's in the slow step. अच्छा इसका बताओ कि अच्छा so it's in the slow step. So the point is that if I increase the concentration of this one, the slow step will speed up. So let's say I double the concentration of the halogenoalkane. So the slow step now takes 50 seconds. It's sped up twice as much. So now the overall speed of the reaction is going to be much faster. That means that it is dependent on the halogenoalkane concentration. It is dependent on the slow step, but it is not dependent on anything that's involved in the fast step. Okay, is that clear?
Yep, that's clear. But how do you know that it's first order, not second order?
Achha, second order. Okay, but right now I'm just talking about 0 and 1. Okay, I haven't talked about the second order right yet. Okay, is that clear? 0 and 1 is clear, right?
Yeah, it's clear.
So this doesn't depend on this, right? So how do you get second order then? Like what? In what way do you get second order? So the previous example was actually a second order example. Okay, I'll move to that one. So this reaction. So let's say let me change the slow and fast step. Let's say it's the other way around. So let's say this one is the first one is your fast step, and the second one is your slow step. So the rate depends on the slow step, right? So the rate depends on these two things, right? That means it doesn't really depend on anything that's involved in the fast step. It's dependent on the reactants that are involved in the slow step. So my rate equation would be that it's so it would mean that it's first order with respect to NO concentration, and it's first order with respect to BR concentration. Rate is dependent on these two things. ठीक है, is that clear?
Yep.
But now there's an issue. And the issue is that this BR over here that I said that rate depends on NO and BR, right? Like if BR concentration doubles, the slow step would speed up. If NO concentration doubles, the slow step would speed up. The reaction would speed up. The only issue is that your BR is an intermediate, which basically means that your BR was actually produced in the previous step. So when I say that the rate of the reaction depends on the concentration of BR, right? BR concentration itself is dependent on the concentration of BR2 and NO. Because if NO and BR2 concentrations are high, then BR's concentration is high, right? So when I say my rate depends on BR, which is an intermediate, it indirectly depends on the first two, right? Is that clear that when I say that rate depends on BR, it actually indirectly depends on these two things? Is that clear?
Yep.
So now I've got now I have no intermediates in my rate equation. But if you look at the equation, how many times is NO appearing in the equation? It's now NO squared, right? And BR2 is order 1. So it means the reaction or the rate of the reaction is actually dependent twice on NO's concentration. Is that clear?
What do you mean by it's occurring twice?
Yeah, initially I said that rate depends on BR and it depends on NO, right? So I wrote it down, right? But then I figured out that BR is an intermediate and BR's concentration depends on these two things, right? So I cut out BR and I said that rate depends indirectly on BR2 and NO. So when I grouped all of them together, I found out that NO is appearing twice. So that means it's going to be NO squared, right?
Oh, okay, yeah.
So that would give you order 2, right? So
Yep.
So what order 2 basically means in the mechanism is that if I double NO's concentration, right, the slow step speeds up because you got NO over there, right? So the slow step speeds up. But if I double NO's concentration, because of NO, Br's concentration would also double, right? So that means Br's concentration in the slow step also doubles. So by changing the concentration of NO, not only do I affect the slow step by changing the concentration of NO, but indirectly it also changes the concentration of Br, which is why it's square. It's like it's going to quadruple, right? So the effect will double, right? Is that clear?
Yep, it's clear.
And vice versa. If I Br, it's only order one. It will only affect it once. So if I increase the concentration of Br2, because of Br2, Br's concentration changes, Br concentration changes, so the rate will be affected, but it's going to be directly proportional. It's going to be order one. That's it. So that's how you find out that if you know the mechanism, right? And that's actually one way of actually figuring out mechanisms. Like you have the slow and fast data. Actually, you have the order data. I mean, you can figure out order using graphs. I mean, you can plot a graph of a reactor and you can see how it's decreasing, whether it's affecting the rate or whether it's not affecting the rate. You can figure out the orders, right? So most of the mechanisms that you see in organic chemistry and elsewhere, they're just basically derived from the order of reaction of the reactant. So I'll just do some. So let me put some questions in front of you. I said just the mechanism part. Just a second. Let me see if we can. So not this one. So यहाँ पे there's a. Let's say this one. So whether try doing this question. This is the overall reaction, right? So that means rate would be either dependent on either one of these three, right? And the three steps of the reaction are given. So let's say the second step is your slow step. Can you figure out the rate equation or the relationship? Like what would be the values of A, B, and C? These are triacro. But are you doing this?
Yeah, I'm trying. So because the second one is the slow equation, so would that mean that I have to firstly put IO minus and H plus and then
Yes.
do the other step? Okay. So then would I put H2O2 and I minus?
Yeah, you're gonna cut out IO minus one, and instead in its place you're gonna put H2O2 and I minus one, right? So that means
Yeah.
first order with respect to all of them, right? Is that clear?
Yeah, that's good.
So try doing the other one, which is, let's say the last one is the slow step.
Is it H plus squared I minus IO minus?
Um, Let me just check. So it's going to be dependent on HY and H plus one and how many were squared?
The H plus was squared.
So now HY was so you get rid of HY, so it's going to be IO minus one and H plus one. So H plus one becomes squared, right? But then the IO minus one is dependent on what? I minus one and H2O2, right?
Oh, okay.
The I minus one also gets squared. So you have to get rid of all the intermediates. Any intermediate that
Okay.
shows up, you replace it with like the IO minus one showed up. So rate is dependent on IO minus one. That means indirectly it's dependent on these two things, right? Is this clear?
Yeah.
Now that's your mechanism, okay? That's your mechanism which is going to tell you what the rate is. Just remember that the rate determining step is the slow step. Anything that's in the fast step, that's order zero. तो यहाँ लिख देता हूँ एक से mechanism. So rate determining step is your rate determining step is your slow step. ठीक है? अच्छा और कोई questions में just a second. अच्छा over here he's plotting. अच्छा over here he's plotting. He's keeping the two reactants constant. I mean, how do you keep them constant? By putting them in large excess. So their concentration almost throughout the reaction remains constant, right? And he plots the graph of I minus one with respect to time. Can you measure the half-life of this graph?
So is half-life like every 30 days it's decreasing by 0.002?
Half-life is how much time it takes for the concentration to decrease by half. So for example, over here it's good.
Okay.
Like over here, that's the first half-life, right?
90 days.
What's the
90
second half?
seconds.
Okay, what's the second half-life? That's half of the previous one, right? So that's again 90 days, right? I mean, this is 90, and this one
because okay, that makes sense.
is also 90. When you have a constant half-life, that means it's order 1. When the half-life doubled, it's order 2. And when it's a straight line, that means it's the speed is not changing with respect to time. So that means the reactant has no effect on its order 0. ठीक है, clear?
Yep, it's clear.
So चलो ठीक है, let's continue tomorrow then, ठीक है? We'll just do the last part and we'll be done with this one.
Okay.
Okay, brother, take care.
Okay, thank you.
Love